For most of human history, the Andromeda Galaxy was nothing more than a faint smudge in the night sky, a mysterious haze that quietly hovered beyond the reach of our comprehension. Ancient stargazers looked upon it with wonder, unsure whether it was a trick of the eye or a whisper of something profound. To some, it was a cloud of celestial mist within our own Milky Way, a nebula cradled in the vast darkness. To others, it hinted at a larger truth, too grand to accept without evidence. But the truth, once it was finally revealed, did more than answer a question. It shattered the boundaries of our understanding. Andromeda, it turned out, was not some local curiosity, not a cloud or a wisp of gas within our galactic borders, but a galaxy in its own right, massive, majestic, and far beyond the limits of what we once thought possible. And as our instruments sharpened and our minds opened, we began to realize something even more astonishing. Andromeda is not only our neighbor in the cosmos, it is also our future, locked in a silent gravitational ballet with the Milky Way. It is destined to collide and merge with our own galaxy, forming something entirely new. What was once a faint blur has become a mirror, reflecting both our past ignorance and our future destiny, and beckoning us to understand not only what it is, but what it means. In the early years of the 20th century, astronomers found themselves grappling with a question that would redefine the scale of the universe. Was the Andromeda Nebula merely a small cloud of gas within our own Milky Way? Or was it a separate galaxy altogether, a vast island universe floating unimaginably far from us? At the time, the consensus was that the Milky Way was the entirety of the cosmos, a self-contained system housing every known star and nebula. Faint glowing patches in the night sky were cataloged as nebulae, assumed to be regions of interstellar gas, perhaps forming new stars within the galactic structure. Andromeda was among these cataloged smudges, notable for its spiral shape, but still considered part of the Milky Way's intricate design. Yet, a few bold thinkers proposed a radical alternative, that Andromeda and other spiral nebulae were not internal features, but entire galaxies in their own right, each composed of billions of stars. The implications were staggering. If true, the universe would be far larger than anyone had imagined, and our place within it far less central. The debate intensified, culminating in what is now known as the Great Debate of 1920, held at the Smithsonian Institution. Harlow Shapley, who believed the Milky Way was vast enough to encompass all, argued against the idea of other galaxies, citing measurements that placed our galaxy's diameter at 3,000 light-years. Opposing him was Heber Curtis, who pointed to dim novae in Andromeda and the structured appearance of spiral nebulae as evidence of great distance and independent galactic systems. Though both men presented compelling cases, no definitive winner emerged from the debate. It would take the keen eye and precise measurements of Edwin Hubble to finally settle the matter. In 1924, Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory, identified Cepheid variable stars within the Andromeda Nebula. These stars, whose luminosity could be determined by their pulsation rate thanks to the earlier work of Henrietta Swan Leavitt, allowed Hubble to calculate the nebula's true distance. The result was astonishing. Andromeda lay more than 2 million light-years away. It could not possibly be a part of the Milky Way. It was a galaxy in its own right. This revelation did more than confirm the island universe theory. It redefined the universe itself. What had seemed an isolated cosmos was now one of countless such realms. And the night sky, once a static canopy of stars, was revealed as a sprawling tapestry of galaxies stretching across incomprehensible distances. With this breakthrough, astronomy entered a new era. The universe was no longer a single galaxy. It was a boundless expanse filled with myriad galaxies, each harboring its own secrets, its own stars, and perhaps its own life. The Andromeda Galaxy, once a source of confusion and controversy, became the symbol of cosmic perspective, a reminder that our knowledge is always partial, and that the universe is always more vast than we think. Yet, even after Hubble's groundbreaking discovery, questions remained. The scientific mind, always curious and rarely content, found itself struggling with new mysteries. If galaxies were so far away, how could they appear so bright? The luminosity required to make Andromeda visible across millions of light-years was immense, suggesting that galaxies housed far more energy than previously understood. At the time, theories about how stars produced energy were still evolving. Gravitational contraction had been the leading idea, but it couldn't explain the longevity and brilliance of stars. Nuclear fusion, the process of hydrogen atoms fusing into helium under immense pressure and releasing vast amounts of energy, was not yet fully established as the engine behind stellar life. Until that theory solidified, the true power source of galaxies like Andromeda remained a mystery. Meanwhile, the observed distribution of galaxies introduced new puzzles. They were not randomly scattered, but often grouped into clusters and filaments, leaving vast voids between them. What force was shaping this cosmic web? Gravity seemed the likely culprit. But detailed studies of galactic motion were still decades away. And then there was the enigma of Andromeda's motion itself. Unlike most galaxies, which appeared to be receding due to cosmic expansion, Andromeda was approaching the Milky Way. This peculiar movement defied the prevailing expectations of Hubble's law, which correlated redshift with distance. The explanation came from the recognition that cosmic expansion operates on large scales. But local galaxies are still subject to mutual gravitational attraction. Andromeda and the Milky Way are close enough that gravity outweighs expansion, pulling them together on a collision course that will culminate in a merger billions of years from now. As astronomers began to look deeper into Andromeda's structure, they discovered a galaxy rich with complexity and history, no longer just a point of light. It became a vibrant system teeming with stars of all ages, clouds of gas, and elusive halos of dark matter. Its core glowed with the warm light of ancient red stars, while its spiral arms shimmered with the blue radiance of newborn suns. In some regions, massive clouds of hydrogen condensed under gravity, triggering waves of star formation. In others, the remnants of galactic collisions painted the sky with streams of stars and disrupted gas. These features told a story of growth through accretion, of small galaxies being drawn into Andromeda's gravitational embrace. Their identities gradually lost as they merged into a larger whole. Beyond its luminous parts, Andromeda was surrounded by a vast, invisible halo of dark matter, a substance we cannot see, but whose gravitational fingerprint is unmistakable. The rotational velocity of stars in the outer regions remained unexpectedly high, inconsistent with the visible mass alone. This implied the presence of a hidden scaffold, holding the galaxy together and hinting at one of the universe's deepest mysteries. The stars and gas we can observe are merely the surface of a far greater structure, shaped by something we have yet to fully comprehend. The more we learned, the more Andromeda emerged as a mirror for our own galaxy. Its central bulge, its thick disk, its spiral arms and satellite galaxies all echoed the structure of the Milky Way. Yet it was larger, more massive, and perhaps more active in the recent past. This similarity made it not only a neighbor, but a prototype, a tool through which we could study our own galactic home. And with the knowledge that Andromeda and the Milky Way are destined to merge, our curiosity took on a new edge. We are not merely observers of Andromeda. We are participants in a shared destiny. In 4 billion years, the two galaxies will collide, their stars mingling, their gas clouds intertwining, and their structures reshaping into a new elliptical galaxy, a transformation as beautiful as it is inevitable. The collision will not be a violent crash, but a slow, gravitational dance, with stars mostly passing by each other, yet reshaping their orbits and forming new generations of stars in the compressed gas clouds that result. It will be a kind of rebirth, a cosmic reinvention that speaks to the rhythm of the universe expansion, collision, renewal. What began as a question nebula or galaxy has evolved into a story of epic scale and intimate resonance. Andromeda, once a smudge in the sky, has become a cornerstone of our understanding, a symbol of cosmic perspective, and a reminder of our own impermanence. It teaches us that the universe is layered in mystery, that our place within it is both fleeting and deeply connected to everything else. And in its approach, silent, patient, unstoppable, we find a metaphor for time itself, carrying us forward into transformations we can barely imagine. The night sky is no longer static. It is a living history of light, motion, and destiny. And Andromeda is not just our neighbor across the void. It is our reflection, our counterpart, and, in the fullness of time, our future self. Shadows in starlight, unveiling the depths of Andromeda. Andromeda, once a smudge in the sky, now unfolds as an intricate tapestry of cosmic history, stellar evolution, and enigmatic whispers of the unknown, inviting us into its spiraling arms where the past and future of galaxies collide. As astronomers turned their gaze beyond the revelation of Andromeda's galactic nature, they found themselves immersed in a galaxy of astonishing richness, a place where the age and vitality of stars, the ebb and flow of gas and dust, and the silent presence of dark matter converged to compose a narrative spanning billions of years. Here, in this sprawling island universe, stars live out lifetimes of blazing glory and quiet fading, their collective light tracing the evolution of a galaxy that has undergone cycles of birth, transformation, and merger. Andromeda's stellar population reveals its layered history. Its dense central bulge glows red with ancient stars, fossil records of a primordial epoch, while its spiral arms shimmer with the blue of young giants, blazing with intensity in cradles of gas and dust. These arms, more than graceful structures, are engines of star formation, where hydrogen coalesces under gravity's pull, igniting into new suns that illuminate their birthplace. Between these regions lies a medium enriched with heavier elements, the ashes of long-dead stars testifying to a galaxy that recycles its material through generations. The process of stellar creation is not uniform across Andromeda. Some sectors teem with hot, nascent stars, while others, starved of gas, lie dormant, remnants of a more active past. This unevenness hints at interactions and mergers, the cosmic collisions that shape a galaxy's fate. Streams of stars and disrupted clouds point to smaller galaxies swallowed by Andromeda, their material absorbed into the larger whole. Yet perhaps the most mysterious component is what cannot be seen, the immense halo of dark matter extending far beyond the visible disk. Its gravitational grip ensures that stars at the edge of Andromeda rotate as swiftly as those near its center, defying Newtonian expectations and demanding a new framework for understanding mass and motion. Though invisible, This dark halo sculpts the very structure of the galaxy, anchoring its components in an unseen web of influence. Within this context of visible and invisible architecture lies the galaxy's central powerhouse, a supermassive black hole, silent now, but once possibly active, having consumed and shaped the inner bulge with its tidal forces. Surrounding this black hole are dense star clusters moving with the velocities that betray the massive gravity lurking in the dark. Even further out, the spiral arms are not static but dynamic, shaped by the gravitational tug-of-war with Andromeda's myriad satellite galaxies. Dozens of dwarf companions orbit the giant, their presence both a relic of formation and a prediction of its future. Some of these satellites, like M32 and M110, have been partially consumed, their stars integrated into Andromeda's halo. Others exist on paths of slow decay, destined for eventual assimilation. Observations of these interactions reveal long arcs and stellar streams, remnants of cannibalized galaxies stretched across the sky, each a testimony to Andromeda's growth by merger, a process both violent and creative. Meanwhile, globular clusters, dense knots of ancient stars, orbit like time capsules, preserving the conditions of an earlier universe within their bounds. Andromeda harbors far more of these clusters than the Milky Way, suggesting a more tumultuous past, or perhaps simply greater mass. Some clusters, intriguingly, do not match Andromeda's general chemical signature, hinting at extragalactic origins, interlopers caught and bound by gravity. Within the disk and beyond, rare and exotic stars offer further insight. Carbon stars, redder than most, pulse with unique light, their atmospheres rich in the elements of life. Luminous blue variables, on the brink of collapse, flicker and flare unpredictably. Hypervelocity suns dart across space at impossible speeds, perhaps slingshot from encounters with the central black hole or expelled by ancient supernovae. The galaxy is not just a field of stars, but a stage for these exceptional lives, brief, dramatic, and revealing. Layered into this structure is Andromeda's chemical fingerprint, traced through spectroscopy of starlight, heavy elements, forged in stellar furnaces and scattered by explosions, paint a map of the galaxy's alchemy. Metallicity gradients reveal that the inner regions are rich with processed material, while the outskirts remain more pristine, echoing early epochs. And within all of this, there are the faint whispers of dust, silicate grains, carbon compounds, complex molecules drifting between stars. This dust, though humble, seeds the birth of planets, shields starlight, and shapes the spectral signature of the galaxy. The chemical diversity of Andromeda is not uniform. It carries the scars and gifts of its long history, from internal evolution to the merger of alien systems. Every measurement, every spectral line, adds a new layer to our understanding. And yet the full picture remains just out of reach. Andromeda's story is told not only by light, but by motion. Doppler shifts reveal how gas and stars rotate, how they fall toward the center or migrate outward. These motions defy simplicity, shaped by bars and warps, spiral waves and gravitational tides. Mapping these flows provides a kinematic portrait, a choreography of billions of bodies dancing to gravity's tune. Even the interstellar medium, the thin gas between stars, moves with purpose, funneled by density waves or shocked by past collisions. In the halo, stars drift in patterns that remember ancient mergers, their orbits tilted or elongated. It is in these details that the galaxy's history is written. A fossil record not of bones but of motion, the combination of structure, motion, composition, and context creates a portrait of Andromeda that is far more than a galaxy. It is a dynamic, evolving ecosystem where stars are born and die, where collisions write new histories, and where even silence in the form of dark matter or inactive black holes exerts power. The instruments that reveal this portrait are as varied as the galaxy itself. Optical telescopes chart the stars. Radio arrays trace the cold gas. Infrared eyes peer through dust. And ultraviolet detectors catch the hot breath of young stars. Future missions, with even greater resolution, promise to peel back more layers, perhaps even resolving individual stars across the galaxy's face, mapping their ages, movements, and compositions in exquisite detail. Each new observation pushes the horizon of knowledge outward, reminding us that no matter how well we think we know Andromeda, it still holds surprises. It is a galaxy that resists finality, that shifts with every new piece of data, that challenges our assumptions about what galaxies are and how they live. And in this resistance, in this refusal to be fully known, Andromeda reflects the very essence of the cosmos: vast, mysterious, and always one step beyond our grasp. As we study this galactic neighbor, we also study ourselves, for in its structure we see echoes of the Milky Way, and in its future we glimpse our own, when the two galaxies will merge in a cosmic embrace, erasing their identities and forging something new. Andromeda, then, is not just a destination of light and dust, but a mirror held up to the universe, and to us a reminder that even in the cold silence of space, there is a story unfolding with every passing star. Cosmic chemistry and rare stars, Andromeda's hidden signatures. Just as human hands sift through ancient soil to unearth the bones of civilizations past, astronomers unravel the elements of galaxies to uncover the stories written in starlight. Andromeda, the great spiral looming beyond our Milky Way, is not merely a collection of stars and gas, but a living archive of cosmic chemistry, an evolving canvas whose every region tells a story of birth, transformation, and decay. The silent signals of its makeup are deciphered not through direct contact, but through the light it casts into the dark. When a telescope captures Andromeda's glow, it carries with it a complex fingerprint of elemental presence. Spectroscopy, one of the astronomer's most refined tools, disperses that starlight into its spectrum, revealing the presence of hydrogen and helium, the two most abundant building blocks of the universe. Yet interwoven in that spectral symphony are subtle lines from iron, oxygen, carbon monoxide, and heavier elements forged in the crucibles of stars. These signals are not only identifiers of material content, they are timestamps. Each element carries a signature of its origin: iron from the cataclysmic heart of a supernova, carbon monoxide from dense molecular clouds birthing new stars, and hydrogen eternal, primordial, the breath of the Big Bang itself. Through spectroscopy, astronomers assess how these elements are distributed across Andromeda, revealing not a uniform spread, but a layered and complex arrangement. The inner regions, close to the bright bulge, show enhanced metallicity, a term astronomers use to describe the abundance of elements heavier than hydrogen and helium. This enrichment is the mark of age, the legacy of countless generations of stars that lived, died, and returned their fusion-forged elements to the interstellar medium. Each generation refines the chemical character of its environment, the outer arms. By contrast, hold younger stars and a relatively purer mix of gases, more hydrogen, less heavy metal, and in many places, Vast clouds where star formation is just beginning, this radial gradient of metallicity acts like rings on a tree, preserving a record of Andromeda's chemical evolution. The tale grows more intricate in the study of isotopic ratios, oxygen-18 to oxygen-16, or carbon-13 to carbon-12. These subtle shifts in atomic configuration tell stories of different stellar populations, different pathways of fusion, and different galactic histories. When compared to the Milky Way, Andromeda shows notable distinctions. The variation in isotopic ratios suggests differing rates of star formation, differing episodes of galactic ingestion, and perhaps even differing beginnings. Where our galaxy has been relatively peaceful in its growth, Andromeda reveals a past marked by upheaval, mergers, and rapid stellar turnover. It is this restless history that accounts for the diversity of its stellar cast. Among that cast are actors both rare and luminous blue variables, massive stars at the edge of stability, pulse and flare within Andromeda's spiral arms. These giants, teetering on the threshold of collapse, live fast and die young. Their brightness can change dramatically in short periods, driven by instability in their outer layers. In them, we see a phase of stellar evolution so short-lived that their observation is like catching lightning frozen in time. Wolf-Rayet stars, stripped of their outer hydrogen envelopes and blazing with the fury of fusion closer to their cores, populate some of Andromeda's most active regions. These stars are the prelude to supernovae, their powerful winds seeding the galaxy with freshly minted heavy elements. There are those who do not stay, hypervelocity stars, flung outward by gravitational encounters or perhaps slingshotted by Andromeda's central black hole, streak across the galaxy with speeds so great that they may one day leave it entirely. Their existence hints at immense energies and dynamic interactions within the galactic core, and in the bulging halo reside the elders' metal-poor stars, some nearly as old as the galaxy itself, whose light comes from a time when heavy elements were scarce. They are fossils from a younger universe, silent witnesses to the dawn of galactic formation. Andromeda's deeper mysteries emerge through its population of compact remnants, stellar corpses that glow with the embers of past violence. Magnetars, rare neutron stars with magnetic fields trillions of times stronger than Earth's, hint at the massive stars that came before them. Their presence in Andromeda indicates epochs of intense stellar birth and death, where the collapse of a massive star did not yield a black hole, but instead an object so dense, so extreme, that space-time itself warps in their presence. When magnetars flare, they release gamma rays and X-rays of unimaginable power, momentarily outshining entire galaxies in their violent cries. Andromeda's skies have, on occasion, echoed with such call. White dwarfs, the quiet remnants of sun-like stars, populate the galaxy in even greater numbers. Some are simple cinders, slowly cooling, but others, locked in binary systems, draw matter from their companions. As this matter accumulates, it can trigger thermonuclear detonations on the surface of nova. These outbursts, bright and sudden, were once mistaken for new stars, yet they are not births, but death throes. Variable white dwarfs, flickering in their luminosity, provide further insights into the physics of matter at extreme densities, their behavior under gravity, magnetism, and accretion continues to puzzle and inspire astrophysicists. Each of these objects' luminous variables, hypervelocity stars, magnetars, and white dwarfs, is a clue to Andromeda's past. They tell of regions where gas condensed rapidly, where mergers compressed molecular clouds into stars, and where the deaths of those stars reshaped the galaxy around them. The chemical and stellar diversity of Andromeda is not a random tapestry, but a memory etched in light, motion, and composition. It is a chronicle of cycles, hydrogen becoming stars, stars creating metals, metals enriching clouds, clouds birthing new stars, and the process repeating in waves of creation and collapse. To study Andromeda is to read a cosmic biography where every chapter is written in atoms and light, from its metal-rich core to its youthful spiral arms, from its brightest variables to its dimmest dwarfs. The galaxy carries within it the memory of everything that has come before, and as it hurtles slowly toward the Milky Way in their destined embrace, its chemical identity, shaped over billions of years, will one day mix with our own, blending histories and elements into a shared cosmic future. The stars of Andromeda may seem far, but in their light we see the universality of matter, the constancy of fusion, and the unbroken line of transformation that links all galaxies in the grand unfolding of the cosmos. Clusters and companions. The galactic ecosystem. From the crowded lanes of Andromeda's starry heart to its distant, whispering halo, black holes move like invisible monarchs, cloaked in silence yet ruling with undeniable force. Though most of them elude direct observation, their presence is revealed through their gravitational imprint on the motion of stars and the bending of light, as if the very geometry of space were a parchment scored by their hidden passage. At the center of Andromeda lies a supermassive black hole, estimated to be 140 million times the mass of the Sun, an anchor so dense and mysterious that time itself falters near its edge, unlike the tumultuous cores of active galaxies that blaze with the fury of material being devoured. Andromeda's central black hole is quiescent, dark, and contemplative, hinting at either a slumbering past or a prelude to awakening. Encircling it is a densely packed cluster of old stars that dance in tight, elliptical orbits, their erratic paths revealing the black hole's titanic mass, a silent sovereign hidden from sight, yet known through the trembling of nearby worlds. But this core is not alone in its gravity-wrought dominion. Scattered throughout the galaxy may be a population of intermediate mass black holes, ghosts of past galactic mergers or collapsed remnants of ancient, massive stars, each subtly shaping their neighborhoods with gravitational whispers. These enigmatic entities, difficult to detect yet fundamental to galactic architecture, may dwell in globular clusters or drift alone through the stellar fields, unchained and wandering. Occasionally, one reveals itself during a moment of cosmic drama, the sudden flaring of a star pulled apart in a tidal disruption event, or the brief, lensing magnification of a background star's light. Andromeda's black holes, though unseen, are felt, like the soul of a song carried by vibration rather than voice. Yet even these dark monarchs do not govern alone. They share the cosmic stage with the most elusive and dominant force in Andromeda's composition: dark matter. Though it cannot be seen or touched, dark matter is believed to comprise the majority of the galaxy's mass, forming a vast, spherical halo that envelops the visible stars like an unseen cathedral. This hidden framework determines the rotation of Andromeda, ensuring that stars in its outskirts orbit faster than they should if only visible matter were present. It is a mystery at the intersection of the known and unknown, an invisible sculptor shaping the structure of galaxies while defying every attempt to be directly captured. Its distribution is not uniform, but clumpy, hinting at interactions with satellite galaxies or the ghostly vestiges of earlier cosmic collisions. Through gravitational lensing, where light from distant objects is subtly bent as it passes through this dark material, Astronomers trace its outline like detectives reconstructing a crime scene from scattered clues. The structure it reveals is not static, but dynamic, flexing and evolving over cosmic time, guiding the birth of galaxies and dictating the flow of cosmic material. Without it, Andromeda's stars would scatter like dandelion seeds in the wind. With it, they coerce into the vast spiraled tapestry we see today. As profound as these invisible forces are, so too is the grand collection of companions that surround Andromeda, its satellite galaxies. More than 4 dozen of these smaller systems orbit Andromeda, from the bright ellipticals M32 and M110 to the faint and ghostly dwarfs scattered across its halo. Their presence is not merely ornamental, but revelatory, providing insight into the history of cosmic accretion and galactic cannibalism. Some are being torn apart, their stars stretched into tidal streams that arc around Andromeda like celestial scars from ancient battles. Others persist in tightly bound orbits, their gas stripped and their star formation stifled by Andromeda's gravity. Strangely, many of these satellites are not randomly distributed, but rather appear to lie within a vast, thin plane, an alignment that challenges conventional models of galactic formation. Are these remnants of a single accretion event, or do they trace the filaments of the cosmic web, pulled in by dark matter highways? Each satellite is a fragment of a deeper narrative, a cosmic relic bearing the signature of gravitational tides and ancient stellar heritage. Some of these dwarfs are nearly invisible, composed almost entirely of dark matter with only a smattering of stars, offering tantalizing glimpses into the boundary between galaxies and the vast unseen realms beyond. Others, though brighter, are slowly dissolving, their stars and gas merging with Andromeda's halo in a process that continues to build the galaxy's mass. The gravitational ballet of these companions not only reshapes Andromeda's outer structure, but also informs us about the nature of dark matter and the mechanics of galactic evolution. Through them, we witness the long, slow dialogue between host and satellite, between the massive and the meek, unfolding over billions of years. As we peer deeper into Andromeda's architecture, our tools evolve in tandem with our curiosity. Mapping such a colossal system is an endeavor both technical and poetic. Like trying to chart the contours of a dream, the Hubble Space Telescope created one of the most detailed portraits of Andromeda ever composed. A mosaic stitched from thousands of individual images that revealed over 100 million stars, each one a pinprick in the canvas of creation. Through spectroscopy, astronomers decode the light of these stars to learn their composition, temperature, and velocity, constructing three-dimensional maps of motion and chemistry. By analyzing Doppler shifts in the light, we trace how Andromeda rotates, spins, and flows, revealing its dynamic essence. Infrared telescopes like Spitzer peer through veils of interstellar dust, uncovering star-forming regions otherwise hidden from view, while radio observatories map cold hydrogen gas through its signature emissions, showing where Andromeda continues to sow the seeds of new generations. Computational simulations allow astronomers to recreate the galaxy's evolution over billions of years, revealing how mergers, gas flows, and gravitational tides have shaped its spiral arms and central bulge. These models, grounded in data but imbued with imagination, help us predict the future as well. In 4-5 billion years, Andromeda will collide with the Milky Way in a cosmic fusion that will give rise to a new galaxy, an elegant but turbulent reshaping of stellar architectures. Even as we map its visible stars and catalog its hidden forces, we are haunted by what remains unknown: the black holes we cannot see, the dark matter we cannot touch, the dwarf galaxies slipping away like ghosts, all speak to the persistent mystery at the heart of the universe. In the story of Andromeda, we see not only the anatomy of a galaxy, but the echoes of our own future. We, too, orbit within a vast spiral, subject to gravity's pull and time's ceaseless current. The stars we observe are both windows and mirrors, reflecting not just what is, but what might be. Andromeda, once a faint smudge in the sky, has become a living testament to the majesty and melancholy of cosmic evolution, a reminder that even in the quiet drift of galaxies, the universe sings with purpose and impermanence. Black holes and dark matter, Andromeda's invisible forces. In the quiet heart of the Andromeda Galaxy, where light and shadow entwine in eternal orbit, lies one of the most enigmatic forces in the cosmos, a supermassive black hole, silent and unseen, yet powerful enough to shape the very structure of the galaxy around it, known as M31. This black hole sits like a cosmic anchor at the galactic center, its mass over 140 million times that of our Sun. Despite its immense size, M31 remains unusually dormant, showing little of the furious activity often associated with the brightest active galactic nuclei. It does not emit the blazing X-ray flares or ravenous particle jets seen in quasars or Seyfert galaxies. Instead, it sleeps for now. Around it, a dense cluster of stars whirls in a gravitational ballet, their orbits betraying the presence of an invisible colossus. The calmness of M31 belies its potential. Should new material fall into its gravitational grip, perhaps the shredded remains of a wayward star or cloud of gas, it could awaken again, unleashing energy that echoes across interstellar space and reshapes the core of Andromeda itself. But Andromeda's black hole is not alone in its depths. Scattered through the galaxy, hidden among the millions of stars, may lie intermediate mass black holes, elusive objects ranging from hundreds to thousands of solar masses, born from the deaths of massive stars or successive mergers in ancient clusters. These intermediate black holes are harder to find, but their gravitational whispers may be caught in the motions of stars within globular clusters, or in sudden, transient bursts of radiation when they interact with nearby matter. Some of them may be relics from galaxies long since absorbed by Andromeda, ghostly remnants that drift in the halo, still shaping their surroundings in subtle but significant ways. The concept of wandering black holes, adrift without a fixed home, adds another dimension to this unseen population, ejected by gravitational slingshots during past galactic collisions, or flung outward in the aftermath of black hole mergers. These solitary travelers may roam the vast outskirts of Andromeda, occasionally disturbing star clusters or altering the paths of entire stellar streams. Debating them directly is nearly impossible. They emit no light, but their presence may one day be revealed through gravitational lensing events or gravitational waves as our instruments become more sensitive. Still, even these black holes, massive as they are, cannot account for all the hidden gravity in Andromeda. That role belongs to something even more mysterious. Dark matter, the invisible scaffold on which galaxies are built. Though it neither emits nor reflects light, dark matter reveals itself through its gravitational influence, and Andromeda is wrapped in an enormous halo of it, a structure far more massive than the visible galaxy itself. Extending well beyond the spiral arms and stellar halo, we know it is there because of how Andromeda rotates. If the galaxy contained only its luminous matter stars, gas, dust, then the outer regions would rotate more slowly. Much like the outer planets in our solar system orbit the Sun at lower speeds. But instead, stars at the galaxy's periphery move just as fast as those closer to the core. This defies classical physics unless there is a hidden source of mass keeping the outer regions gravitationally bound. The only plausible answer is dark matter. By mapping the rotation curves of stars and gas, and by observing how light from background galaxies bends as it passes through Andromeda's halo, a technique called gravitational lensing, astronomers have slowly pieced together the dark silhouette of this cosmic phantom. What emerges is a clumpy, irregular halo of enormous extent, shaping the behavior of satellite galaxies, bending starlight, and determining the very fate of the local group. The dark matter in Andromeda is not uniform. Some regions are denser, perhaps shaped by ancient mergers, by the gravitational tug of companion galaxies, or by substructures that once belonged to galaxies now consumed. Its presence affects the orbits of dwarf galaxies like M32 and M110, and may even dictate the shape of Andromeda's disk and halo, but its influence does not stop there. It reaches beyond, extending tendrils of gravity into the space between galaxies, binding Andromeda and the Milky Way in a slow, inevitable collision. This grand merger, projected to occur in about 4-5 billion years, will be one of the most significant events in the history of both galaxies. The visible interaction stars flung into tidal tails. Gas clouds colliding to form bursts of new stars will be dramatic, but even more profound may be the unseen dance of dark matter and black holes. As Andromeda and the Milky Way spiral toward each other, their dark matter halos will interact first, passing through one another like ghostly veils, gravitationally warping each other, altering trajectories, and guiding the galaxy's final approach. When the galactic disks collide, their central black holes may eventually find each other, orbiting closer and closer in a death spiral that will send ripples of gravity across the universe, a final cosmic heartbeat from the dying days of two great galaxies. The new galaxy formed Milkomeda will not simply be a blend of stars and gas, it will carry the signatures of both progenitors' dark matter halos, now interwoven into a single gravitational structure. How this merger of invisible mass unfolds could reveal whether dark matter interacts only through gravity or if it possesses deeper, unknown properties, a question that remains at the forefront of theoretical physics. Some models predict that self-interacting dark matter could clump, collide, or dissipate differently than standard cold dark matter, leaving distinct fingerprints in the resulting galaxy structure. Others suggest dark matter is made of axions, sterile neutrinos, or yet unknown particles, each with unique implications for Milkomeda's future evolution. And what of the black holes? The central black holes of the Milky Way and Andromeda Sagittarius A and M31 will likely spiral inward through dynamical friction, eventually merging in a titanic explosion of gravitational waves. The resulting black hole could be tens or hundreds of millions of solar masses, forming the dominant heart of the new galaxy. Meanwhile, the population of intermediate and wandering black holes, stirred by the galactic collision, may migrate toward the center, be ejected into deep space, or settle into new orbits, reshaping the internal dynamics of Milkomeda for billions of years to come. From the tranquil center of Andromeda to the dark tendrils that stretch far into intergalactic space, from quiet black holes waiting to awaken to vast clouds of unseen mass steering the fate of stars. These invisible forces are not just background features, they are the architects of cosmic destiny. We may never see them directly, but their fingerprints are everywhere in the spin of a galaxy, in the motion of a star, in the very structure of the cosmos. To understand Andromeda is to glimpse the hidden skeleton of the universe, the secret framework upon which everything we know is built, and in the silence of its black holes and the whisper of its dark matter, we hear the deep pulse of time itself, echoing across billions of years, shaping not just galaxies, but the story of all existence. Mapping the giant, observing and simulating. Andromeda. For centuries, the Andromeda Galaxy remained a distant enigma, a glowing smear of light barely perceptible. In the night sky, too far to reach yet too bright to ignore, and as the tools of astronomy sharpened, so too did our vision of this colossal neighbor. Until we could no longer simply observe it, we needed to map it, understand it, and predict its future. The effort to chart Andromeda began in earnest with the Hubble Space Telescope, which embarked on an ambitious project to construct a mosaic of the galaxy so vast and intricate that it would capture millions of stars in a single panoramic view, thousands of separate exposures, painstakingly stitched together over years, revealed a glittering expanse filled with stellar populations of all ages. Hubble's work didn't stop at imaging. By measuring Doppler shifts in the light of Andromeda's stars, astronomers traced the galaxy's rotation and the movement of its stars, uncovering the subtle dance of gravitational forces that dictate its structure. Motion tracking revealed not a static object, but a dynamic system, twisting and turning as it draws in smaller galaxies and prepares for a cosmic rendezvous with the Milky Way. To see beyond the shroud of interstellar dust that veils Andromeda's more obscure regions, scientists turned to infrared telescopes like Spitzer, whose vision pierced through the opacity to expose the hidden birthplaces of stars. These observations were complemented by radio instruments such as ALMA, which detected the faint emissions of molecular hydrogen, the raw fuel for stellar creation. By mapping these emissions, astronomers traced the distribution of gas across the galaxy, charting the cosmic reservoirs that sustain Andromeda's continuing evolution. Particularly vital was the detection of the 21-centimeter hydrogen line, a specific radio frequency emitted by neutral hydrogen atoms, which allowed researchers to peer through dusty regions and map the structure of the galaxy's disk in unprecedented detail. These techniques together painted a portrait not just of where stars are, but of where they will be born, revealing the galaxy's evolving blueprint. Yet even the sharpest eyes of our telescopes couldn't fully capture the intricate past of Andromeda. That's where simulations stepped in, leveraging computational power and physical laws. Scientists built virtual models of the galaxy, inputting data from observations and running the clock both backward and forward in time. These simulations showed how Andromeda's present form was sculpted by ancient collisions with smaller galaxies, each leaving behind tidal streams of stars and disrupted structures. They also projected a dramatic future, a head-on collision with the Milky Way in about 4–5 billion years. The simulations visualize this event not as a cataclysm, but as a cosmic ballet, where the two galaxies will interlace, tear at each other with gravity, and gradually coalesce into a single elliptical entity, Milkomeda. Within this vast simulation, stars slingshot into new orbits, gas clouds compress into bursts of new star formation, and black holes spiral inward, dancing toward union. The need to refine these models and to prepare for what's to come drives new missions. The upcoming Nancy Grace Roman Space Telescope promises to extend our vision even further, with wide-field infrared capabilities that will allow it to map large regions of Andromeda in exquisite detail. It aims to detect faint structures hidden in the outskirts of the galaxy, trace its population of rogue stars and elusive black holes, and unlock more clues about dark matter's role in shaping its gravitational contours. Meanwhile, continued radio observations will deepen our understanding of Andromeda's gaseous halo and its magnetic field, two features that still elude comprehensive explanation. Even with all we know, Andromeda remains a puzzle, each new discovery deepening the mystery rather than solving it entirely. In the interplay of observation and simulation, of light and shadow, of matter seen and unseen, we inch closer to understanding this giant, and though we remain rooted on Earth, we extend our reach into the cosmic dark, guided by Andromeda's luminous pull and driven by the human need to chart the unknowable. The map is not yet complete, but in its incomplete form, it tells us just how much more there is to see. And so, our journey draws to a close not with finality, but with an open horizon. In mapping Andromeda, we have done more than measure the distance between stars or calculate gravitational arcs. We have reached across time itself, touching remnants of a galaxy's past and glimpsing the future shape of our cosmic kinship. From the quiet shimmer of ancient metal-poor stars to the invisible grasp of dark matter halos, Andromeda stands not just as an object of study, but as a mirror reflecting our own galaxy's fate and perhaps our place in the grander design. As we have peered into its depths, traced its spirals, and imagined its eventual embrace with the Milky Way, we have been reminded that even the mightiest structures in the cosmos are impermanent, caught in a rhythm of creation, collision, and transformation. What began as a smudge in the night sky has become a symphony of stellar lives, magnetic winds, hidden engines, and elemental echoes, all converging into a narrative that stretches across billions of years. In Andromeda, we find not just the story of another galaxy, but the prologue to our own unfolding chapter in the cosmic epic. And as the light from its stars continues to reach us, so too does its call to keep looking, keep questioning, and keep wandering toward the unknown.